In this lesson, we'll look at the IPv6 address format, the different parts of IPv6 addresses, and some of the features that they have over IPv4. IPv6 uses a 128-bit address that's comprised of 8 16-bit blocks, each containing 4 hexadecimal numbers. Each block is separated by a colon. With IPv6 being a 128-bit address, that gives us 2 to the 128th power, or approximately 340 undecillion available IPv6 addresses. Thankfully, though, there are some rules we can use to simplify things. In most cases, an IPv6 address has one or more blocks that consist of all zeros. When this is the case, we can remove any consecutive blocks of zeros and replace them with a double colon. But this can only be done once per IP address, and the blocks of zeros need to follow each other. So even though we could have removed this block, it was more advantageous to simplify 2 blocks instead of just 1. The next rule is that we can remove the leading zeros from any block, but only if they're at the beginning. Any other zeros have to stay where they are. This also means that if a block has all zeros, we have to leave 1 0 if the block wasn't eliminated using the first rule. This leaves us with this simplified IPv6 address that's easier to read and work with. Now that you know how to simplify an IPv6 address, let's look at the different parts that make up this addressing standard. An IPv6 address is divided into 2 parts right down the middle. The left part is known as the prefix, while the right part is the interface ID, also known as a token. The prefix can be compared to the network ID in an IPv4 address, while the interface ID is comparable to the host ID. The prefix can be broken down into different components as well. The first 48 bits of the address is defined as the site prefix. The site prefix defines the location and is assigned by the local internet service provider, or ISP. The next 16 bits are the subnet ID. This is the equivalent of the subnet mask in an IPv4 address and tells us which network we're connected to. As mentioned earlier, the last 64 bits in an IPv6 address is the interface ID. This is a unique identifier we use to define the host. This ID is either automatically configured from the interface's MAC address or manually configured by a person. When the MAC address is used, the interface ID is considered to be in a EUI64 format. Let's see how this works. The first step is to take the MAC address of the computer where this ID will be assigned and converted to binary. Next, the 7th bit from the left is flipped. This means that since this number is a 1, it now becomes a 0. Had it been a 0, it would have become a 1. This new binary number is now converted back to a hexadecimal number. But this is still only a 48-bit address, so the value of FFFE is inserted in the middle, which brings our length to required 64 bits. If we insert the colons in the right place, we see that we now have our IPv6 interface ID. Using the MAC address to generate the interface ID almost guarantees that the IPv6 interface ID will be unique. The interface ID can also be generated using a special algorithm that randomizes its numbers. Not everyone has made the switch from IPv4 to IPv6, so you need to make sure that the 2 protocols can coexist with each other. One option is to use a dual stack configuration. A dual stack configuration simply means that each device's network card is able to support both IPv4 and IPv6. Meaning that these devices can transmit and receive both IP versions in parallel, allowing for greater flexibility. Dual stack works great when we're on the same network, but there may be times when packets need to travel through networks that don't support IPv6 at all to reach their destination. To make it through these hops, we utilize a feature called tunneling. Tunneling is when a packet is wrapped inside another packet so it can travel to where it needs to go. Depending on the situation, there's a few different tunneling methods we can implement. The first method is called Teredo tunneling. This is used to send IPv6 packets from one host to another through an IPv4 network. To do this, the sending host encapsulates the IPv6 packet inside an IPv4 packet. When the receiving host gets the packet, it handles a de-encapsulation process. Moreto tunneling is a variation of Teredo tunneling that's used on Linux systems. Next, there's the 6-to-4 tunneling, which is similar to Teredo tunneling in that we send IPv6 packets wrapped in IPv4 packets. The difference is that instead of the host handling the encapsulation, the routers that sit on each network's end handle that process. 4-to-6 tunneling works much like 6-to-4 tunneling, except it connects two IPv4 networks through an IPv6 network. Finally, we have intersite automatic tunnel addressing protocol tunneling, or ISATAP tunneling. This is used when there are two sites within the same network, but one is using IPv4 and the other is using IPv6. In this case, the router itself is a dual stack router running both IPv4 and IPv6. Hosts on the IPv4 network only understand IPv4 packets, so they send IPv4 packets to the ISATAP router. The ISATAP router takes these packets and converts them into IPv6 packets to be sent to the IPv6 network. The router does the same in reverse, converting the packets from the IPv6 network into IPv4 packets. ISATAP is designed only for intrasite implementations and isn't used to transmit data over the internet. That's it for this lesson. In this lesson, we first looked at the format of an IPv6 address and how we can remove certain zeros to shorten it. Then we looked at the different IPv6 address parts, including the prefix ID and the interface ID. And finally, we went over some IPv6 features, including dual stack configurations and different tunneling options.